Welcome to another lesson from Transparent Physics. The focus for today is on vertical loops. Vertical loops are a subset of a topic often found under uniform circular motion, where the object is spinning in what we call the vertical plane. I'll show you a picture here in just a minute to clarify that. Vertical loops can be a challenging topic, but if you invest the time to understand them, they unlock a lot of very interesting applications that we experience in the world around us. So let's take a look at vertical loops. As soon as we have a sip of tea. All right, let's get started. So, what is a vertical loop? Well, let's start by saying what it's not. Let's focus on the idea of horizontal loops. A horizontal loop, I sometimes call it a helicopter loop. The idea is you're spinning it around in a horizontal circle. It's in the horizontal plane. Now, the idea of a horizontal loop is now the centripetal force is changing direction. It's always pointing towards the center, and because this object is spinning around, the direction of the centripetal force is always changing, but it's always pointing towards the center, and it's always acting in the horizontal plane. Now, this kind of scenario is a great way to start. The earlier problems we worked in this unit were all horizontal loops because you don't have to worry about really the weight factoring in that much because it acts down in a vertical plane. The centripetal force acts in the horizontal plane. And as you may recall from your study of forces, in order to influence the motion of an object, the force needs to be acting in the same direction as the intended acceleration. So a vertical force cannot impact a horizontal acceleration. So the weight doesn't come into play, so it's a nice uniform force given all other things considered equal. Okay, next up is the vertical loop. The vertical loop, I did a little jump cut there just because I started explaining it without moving it into the camera. So a little bit of a jump cut there. I do apologize, but we'll start over here. So a vertical loop, the idea is that you're spinning it in front of you. The weight is always acting down, regardless of where you are. The centripetal force is always acting towards the center. Now, the weight is always acting, say, in the negative y direction, if we want to argue that. The centripetal force could be acting in the x direction, could be acting in the y direction. It depends on where it is. Basically, the idea is that weight is something that sometimes is going to help you, and sometimes it's going to work against you. And we'll go into that in a little more detail in a second, but that's what makes the sensation of spinning around in a vertical loop a little more complicated because it's not consistent like a horizontal loop is. All right. Now, in our sample scenario, we've got an object being spun on a rope, and we can just look at it in terms of two forces. The tension from the string. The tension from the string is pulling inward. That's what strings and ropes and those sort of things do. They pull inward. So the string is always oriented between your hand and the object, and that string always extends radially out from your hand, and the direction of the force is always directed inward along that path. So even though its direction is constantly changing, it is always pointing towards the center of the circle. In comparison, we have the weight. And the weight is always acting on the object, and the weight is pulling downward. No matter where it is in the loop, the weight's pulling downward. So we have these two forces. Tension is always pulling towards the center. Weight is always pulling downward. And despite the fact they're both always doing, the tension always pulls towards the center. Weight always pulls downward. But when they interact, you can get a lot of different things going on. Sometimes it's good for you, sometimes not so good. And when we look at different parts of the circle, we will see that there are a couple different benchmark scenarios that we want to study to try to get a sense of how the forces interact at different points in the circle. So, let's pay the rent. When I talk about traveling in a circular path, I use the metaphor of paying the rent. Hopefully it'll be useful to you as we talk through it as well. Okay. Now, when we deal with objects moving in a circular path, we are going to assume the same conditions of uniform circular motion that we have assumed for the rest of this unit. The object spinning at a constant speed. The radius is also constant. So the centripetal force needed to keep it moving in a circle will therefore be constant as well. And we'll assume the mass of the object isn't changing. Of course, the centripetal force is equal to the mass times the acceleration, where acceleration is v squared over r. Since neither mass nor speed nor radius change, the centripetal force is always the same. No matter where it is spinning in the circle, you always have to have that same amount of centripetal force, whatever it is for that scenario. In circular motion, as we started off at the very, very beginning of the unit, we discussed the idea that you must have a centripetal force, which is an unbalanced force acting towards the center, if you want to have circular motion. If you don't have that circular force, you're not going to move in a circular path. So when it's all said and done, there must always be an unbalanced force acting towards the center equal to whatever this value is. Now, it's going to vary from scenario to scenario, but we can figure out what the value would be. If you don't pay that cost, you are not going to travel in a circle. You must provide that force, when it's all said and done, an unbalanced force acting towards the center. If you can't pay that, you don't get to go in a circle. Now, for this scenario, we're going to assume that you are going in a circle, so you are always going to make the payment. The question is, how are you going to go about doing that? Now, in looking at this, we'll take a look at what's the best way to do this? How about this? Okay, so here's our situation. And we'll try to center it a little better here. And then once we're in there, we'll see if we can zoom in a little bit to get the details a little better. Yeah, I think we can do that. All right, so here's our circle. And the idea is that we are looking at it at 3 different places. Now, there's a myriad of places that we could study it at. We'll just study the 3 interesting points. If you've got astute eyes, I do apologize. There's a couple smudges on the picture. If you're left-handed, you'll understand. So, we are going to, just for the sake of numbers, assume that the centripetal force for our scenario is 100 newtons. And the weight of the object is 60 newtons. I'm not going to defend that mathematically. I just picked 2 numbers that I thought were easy enough to work with for our example. In the drawing, the green arrow represents the centripetal force, and I tried to draw it the same length in each scenario. The centripetal force is always the same. It doesn't matter where it is in the circle. You must provide 100 newtons of centripetal force in order to go around the circle, spinning in this direction. What makes up that centripetal force? The centripetal force, remember, is not a force in and of itself. It's a name we give to forces, or single force, that acts in a way to cause an object to move in a circular path. So centripetal force is a name that we give to other forces that are serving in that role. In this case, our 2 options are going to be the tension and the weight. Now, sometimes they work together, sometimes they work against each other, sometimes they ignore each other. But these are our 2 options. These are the 2 forces that act on the object. So these are the only 2 ingredients in the recipe, if you will. Now, at the top of the loop, we have to pay 100 newtons. At the top of the loop, weight is acting downward. So we have to pay 100 newtons acting downward. And the weight is already like, hey man, I got this, I'll help you out. So the weight's there, and the weight provides 60 newtons acting downward, because that's what weight does. Weight pulls downward. So you have to pay 100 newtons acting down. The weight covers 60 newtons of it. So you're left paying for 40 newtons on your own. That's the amount that the string or the rope needs to pull down with to pay the total rent. The rent is 100 newtons. Weight provides 60 newtons of it. The rope provides 40 newtons of it. So we meet our total 100 newtons, and this object can move around the path. At this point in the loop, the weight is acting downward. And as we mentioned, a downward force in the y direction is not going to be able to provide an acceleration in the x direction. They're in perpendicular to each other, so a vertical force is not going to provide a horizontal acceleration. So here the weight is not providing any assistance. So you're kind of looking around for the weight. The weight's not really there to hang out. So you're like, oh, I guess I'll cover the rent. So you, if you're the tension, are the only force acting in the horizontal direction. So you have to be the force that provides the centripetal force. The tension provides the centripetal force. The centripetal force hasn't changed. Every time we look, the rent is the same. It's a rent-controlled circle. So the tension has to pay the entire 100 newtons. So you can see that as we curl down the loop, the amount of force that you need to exert with the rope increases. At the top of the loop, the weight covered part of it. Halfway down, the weight's not helping you anymore, so you have to provide all of it. Okay. The argument here is that since weight is not contributing to your circular path, you have to provide all the force yourself with the rope. And then finally at the bottom, all right, so the amount of force you have to pay, I'm going to zoom in a little bit again, but we'll zoom out again in a second. You still have to pay 100 newtons. Now at the bottom, right when you're about to pay the rent for this part of the circle, weight comes up to you and it's like, oh man, hey, I got in a little bit of trouble. I need to bump 60 newtons off you. And you're like, dude, I was just about to pay the rent. He's like, hey man, I really need it, otherwise I'm going to be in trouble. So you're like, oh my god. So you pay the debts that weight has collected. Okay, the weight, if you notice, is acting in the opposite direction you need to. So you need to cover this cost before you can even think about accelerating it upwards. This is an unbalanced force acting upward. So before you can have an unbalanced force acting upward, you definitely have to take care of the force that's acting downward. So you basically have to pay off the debt of the weight. So at the top, 60 newtons acting down helped you. At the bottom, 60 newtons acting down counts against you. So at the bottom, the calculation, similar but not identical, is that the weight is working against you instead of with you. So the centripetal force never changes, the weight never changes, but its orientation with respect to where you need to be going is in the opposite direction, so that changes the plus to a minus. In order to pay off the weight's debt and still have 100 newtons left for the rent, you need to come up with 160 newtons. So at the bottom of the loop, it is going to feel heavier because you need to provide both the centripetal force to keep it going in a circle and for the weight. That's why if you were spinning, say, a bucket around in a circle, or if you spin in a loop-the-loop in an amusement park ride, you are going to feel heavier at the bottom because the seat is pushing up on you with more force. Here, it's the tension in the wire. This could easily be the normal force from the seat pushing on you as you go around a loop. As you're at the top of the loop, the seat pushes on you less, then more, and then a lot at the bottom of the loop. So at the bottom of the loop is where you feel the most force acting on you from whatever's acting towards the center. Okay? So, a little metaphor to help us understand the idea. There are lots of applications of this in let's say the Air Force, amusement park rides, things like that. What we're going to do is we're going to cut to a spreadsheet in just a moment, and I'm going to show you some of these numbers worked out in a little more detail, and we'll be able to fiddle with the numbers and show you some of the implications and applications of this math. Okay, we made the switch to Microsoft Excel. Here is my sheet that's handy for calculating vertical loop scenarios. On the top here, you can see we can set it up to adjust the initial information, the radius, the speed, and the mass. Those things work together to get us our calculated information. The mass is going to give us our weight. The radius and the speed are going to give us our centripetal acceleration via v squared over r. And the big value here is the centripetal force, which is the mass times the acceleration. So for instance, if I change the mass here, then the centripetal acceleration is 10 meters per second squared, and the centripetal force is 10 times 2, which gets us 20 newtons. So 20 newtons would be the key number we're looking at here, the key measurement. That's the rent, as we say, that's required to keep us going around the circle. In this particular set of numbers, we can see something not dissimilar to what was just talked about in the video. In this case, the required force is 20 newtons at the top, and hey, lo and behold, the weight provides 20 newtons of force. So if you need 20 newtons of force pointing down towards the center, and the weight provides 20 newtons acting down towards the center, you really don't need to provide any force at all in the rope. If you were spinning something around in a circle like this, you would feel the rope basically go slack just for an instant at the top there. If you were riding in a roller coaster instead of the tension, we could replace Ft by the normal force, where the normal force is the force that's the seat pushing you towards the center at all points in the ride. In this case, the normal force would need to provide very little force, if any, to keep you going around the circle, so you'd feel as if you're kind of dropping out of your seat for an instant. We can manage that sensation based on the information that we provide in terms of the radius and the speed. At the side of the loop, we talked about the idea that the weight is not acting in the same direction as our need for the centripetal force, so the weight doesn't help or doesn't hurt. We're left with needing to cover 20 newtons of force. That means the rope needs to provide that 20 newtons of force. So if we were spinning this bucket, we would feel almost nothing on the rope. Then the slack would pull, and we'd have to feel whatever the normal weight is, basically. And then at the bottom, it's going to feel heavier to us. That's because at the bottom, the weight is acting down. So as mentioned earlier, we still have to pay 20 newtons. The weight is acting down, impairing our ability to do so. So we need to first pay off the weight, 20 newtons acting down, and then we need to provide another 20 newtons acting up so we can still make it around the circle. So the total amount of force here is 40 newtons. So we go from basically no force required at all to just the centripetal force to the centripetal force plus the weight. Now we can change this scenario around. We can make it harder or easier depending on how we want to do it. We can add to the mass, and let's say, for instance, that we make the radius a little bit tighter. That's going to make it harder to get around the circle, and let's increase the speed a little bit too. So we can end up with a situation here where now you need to pay 146 newtons to get around the circle. Now our weight is, say, 39 newtons. So here at the top of the loop, you are still going to be feeling like you have to exert a lot of force because you need 140 newtons to swing that thing around a circle. Weight is helping you, but it's only helping you with about 40 newtons, so you're still left with around 100 newtons to exert. So the weight here is making your job easier, but it doesn't have to make your job nothing. It can simply reduce it. At the side, things are still the same. The only force acting towards the center is the rope, so that is the centripetal force. And at the bottom, again, now the change is not as dramatic because the centripetal force is pretty large, but you'd still have to fight against the weight in order to do that. So instead of paying 146 newtons, you're paying 185 newtons, accounting for the weight. So you're still in the same scenario,
It's going to feel the lightest at the top, it's going to feel the heaviest at the bottom, but the larger acceleration and centripetal force changes the nuances of how those forces kind of play out. If this was a roller coaster ride, you would feel pushed against your seat the entire time. You'd feel pushed against your seat at the top, you feel pushed against your seat at the side, and you feel pushed against the seat at the bottom, because remember, instead of the tension, it would be the normal force. And the normal force is always exerting a force on you. What if we take it the other way? What if we slow down a lot? If we slow down a lot, that's going to reduce the required acceleration. And if you go around a loop too small, or too slowly, if you're spinning a bucket around and you slow down and you slow down and you slow down, eventually that bucket is no longer going to follow the circle. So in this case, let's take a look. The rent that is due here, I tell you what, let's even, there we go, we'll do this. All right, so in this particular set of numbers, the weight of the object is still 39.2. So we're spinning it around in a circle, and the weight pulls down with 39.2, but for these given circumstances, the rent, if you will, is only 28.4 newtons. So the fact is, gravity doesn't care, it's still pulling down at 39.2, but you only need 28.4. If this was the case, if you were spinning something around in a circle, this object would actually begin to fall in tighter than the radius of the curve. You'd actually begin to fall out of the seat or out of the bucket. And depending on the nature of the interaction, the water could begin to slosh out of the bucket. You might, if you were in a roller coaster, obviously there's going to be a harness or a bar or something like that, but you might feel as if you're pressing against the bar. You'd feel as if you're ready to fall down, because gravity is actually doing more force on you than is required for the circle. And the way that physics works means if you have more force pulling down on you than you need, it's still going to accelerate you downward. It's just going to accelerate you downward at a larger rate than is required for the circle, so you're going to fall out of that circle, basically. Again, same thing happens on the side, same thing happens on the bottom. Again, you need the least amount of force at the top, medium amount of force at the bottom, and then the largest amount of force, medium amount of force on the side and the largest amount of force in the bottom. If we can adjust these numbers a little bit, it's sort of an interesting situation. Basically, what we want to see is the centripetal acceleration. That's kind of the magic value, is when the centripetal acceleration works out to around 9.8. All right, so that's pretty much it right there. That might be about as much as I can get without nuancing that any further. When the centripetal acceleration is equal effectively to g, that's that benchmark boundary condition where you have just the perfect amount of force to get you around the top of the loop, supplied only by the weight. That's when the rope will just start to go slack. That's an amusement park ride when you'll just start to feel like you're falling out of the seat. If the acceleration becomes, if we increase the acceleration, then the amount of force gets larger, the centripetal force gets more, your weight hasn't changed, so you need more force acting on you from the seat or the bucket. If the speed gets slower, then gravity pulls down too hard on you compared to what's necessary, and the rope begins to go slack, or you begin to fall out of the roller coaster ride. So it's a kind of complicated situation with vertical loops, but if you stay focused on the specific forces, you can see how those play out. You don't need any of these like centrifugal forces to explain what's going on. You can explain everything by simply looking at the tension and the weight and seeing how they combine together to give you the centripetal force. I appreciate you spending some time with us for this lesson on vertical loops, and I hope with transparent physics we've made things a little clearer.